There's been a lot of misinformation and needless alarm about 3i Atlas and its recent acceleration. In this video, I want to cut through the noise and explain step by step what the data actually show and whether any of it points to something extraordinary, like an intelligent object observing us. On October 29th, right at its closest approach to the Sun, 3i Atlas began accelerating in a way that gravity alone can't account for. NASA's Jet Propulsion Laboratory filed a report showing the object is about 4 arcseconds away from where a gravity-only model places it. That may sound tiny, but when you're tracking something roughly 203 million kilometers from the Sun, that offset is enormous. The measured acceleration is about 0.02 millimeters per second squared. To put that into perspective, over the course of a single month, that tiny, steady push is enough to move 3i Atlas roughly 80,000 kilometers off its expected path. And the acceleration isn't purely radial. It has two components. It's being pushed away from the Sun at roughly 135 kilometers per day squared, which works out to about 60,000 kilometers per month, and it's also moving sideways at about 60 kilometers per day squared, another 27,000 kilometers sideways. So it's not drifting in one simple direction. It's being nudged outward and sideways at the same time. Before anyone panics, this deviation does not send 3i Atlas toward Earth. The change in trajectory isn't sufficient to put it on a collision course with any planet in our system. The next notable planetary encounter on its projected path is with Jupiter, where it's expected to pass in March 2026. So, what exactly do scientists mean by non-gravitational acceleration? Think of it like this. When you throw a ball, gravity dictates a predictable arc. If the ball suddenly had tiny rockets firing on one side, it would veer off that expected path. That's essentially what's happening here. 3i Atlas is not following the path the Sun's gravity alone would produce. Something else is pushing it. For most comets, the natural explanation is outgassing. As sunlight warms volatile ices, those ices sublimate into gas and escape, producing jets that act like mini rocket engines. That's a familiar, well-understood process. The problem for 3i Atlas is the sheer amount of gas that would be required to produce the observed acceleration. This is where the physics gets fascinating. Harvard astronomer Avi Loeb ran the numbers. If you know the acceleration and you have an estimate of the object's mass, you can calculate how much material would need to be expelled to create that push. 3i Atlas weighs at least 33 billion tons. It's enormous compared with the first two interstellar visitors we discovered. It's somewhere between 1,000 and 1,000,000 times more massive than Oumuamua or Borisov. Its nucleus is estimated to be about 3.5 miles or almost 6 kilometers across. With that mass and the measured acceleration, the calculations lead to a striking conclusion. To produce this push through normal outgassing, 3i Atlas would need to lose at least 1/6 of its entire mass during the month around perihelion. That is at least 5 billion tons of gas. Put bluntly, that amount of material would form a massive, blindingly bright cloud around the object, a cloud our telescopes would not miss. From late November 2025 through late January, dozens of ground-based observatories, along with space telescopes like Hubble and the James Webb Space Telescope, will be watching 3i Atlas closely. On December 19th, it makes its closest approach to Earth at about 167 million miles. If that predicted colossal gas cloud exists, we'll see it then. If it doesn't, the natural outgassing explanation will be in trouble. And that's where the scientific conversation gets truly interesting. If the needed cloud is absent, we have to seriously consider other mechanisms, physical processes we haven't modeled well, or, reluctantly, the possibility of engineered activity. It's important to stress that scientists are not declaring 3i Atlas to be alien technology. The point is one of method. When carefully measured data disagree with current theories, you have to take the data seriously and follow where they lead, even if the implications are uncomfortable. You don't get to dismiss observations simply because your models can't explain them. We've seen echoes of this before. The first interstellar object, Oumuamua, also displayed non-gravitational acceleration without showing any detectable gas or dust. Even the very sensitive Spitzer telescope couldn't find outgassing. Some researchers labeled it a dark comet, which is somewhat contradictory. Comets, by definition, produce tails. Now 3i Atlas presents a pattern that's even stranger than Oumuamua's. It has additional anomalies that make the natural explanation harder to accept. First, there's the brightness behavior. As 3i Atlas approached the Sun, its brightness increased following a power law with an exponent near -7.5. For non-specialists, that means it brightened far faster than normal comets, which typically follow a power between -2 and -3. In short, 3i Atlas became bright at a rate more than double what we would expect, unprecedented for a comet. Second, and this is listed as one of the anomalies, 3i Atlas appears bluer than the Sun at closest approach. That is odd because dust normally reddens reflected light. Cold surfaces don't glow blue. The surface temperature of an object that far from the Sun should produce redder, not bluer light. A natural explanation might be ionized gases, such as carbon-bearing molecules emitting light directly, which can produce bluer colors, but again, the required quantities don't add up with the missing cloud. So where does that leave us? The responsible scientific stance is clear. Collect more data, make testable predictions, and then see which hypotheses survive. If a massive debris cloud appears, the case for outgassing is strengthened and the mystery resolves into an extreme but natural cometary behavior. If it doesn't, we must broaden our search for explanations, from uncommon physical processes and fragmentation scenarios to cautiously, and only if the data demand it, possibilities that involve active or engineered mechanisms. Avi Loeb's broader point, which deserves repeating, is about scientific integrity. When the measurements don't match our theories, the right response is not to dismiss the measurements, but to investigate them thoroughly. He's told the story of a conversation about the Hubble tension, different measurements of the universe's expansion rate, where some scientists preferred to assume the data were wrong because they lacked an explanation. That's not how science progresses. We have to let the data guide us. Whatever 3i Atlas turns out to be, the coming weeks will be decisive. The telescopes are ready, the predictions are clear, and December 19th will give us a crucial test. Until then, the right attitude is curiosity balanced with rigor. Watch the sky, follow the evidence, and be prepared for whatever the universe shows us next.